spent the last couple months running tests on this Billet Labs Monoblock, which is a combined CPU plus GPU water block solution that's intended to compact the system into as much of a pancake as physically possible. Now, in the course of testing, we began with a prototype from the company, that's this one here, and eventually they made what is effectively their production-ready model. That's the one we have mounted now. This testing included use of our new laser scanner, which creates a 3D image of the surface that allows us to see microscopic imperfections and surface finish quality. And we're planning to introduce that for our CPU cooler reviews going forward as well, where it'll basically replace our old flatness testing, which we did with a needle. Now we're going to be doing it with a laser. So you'll see more of that machine in the future. Additionally, we ran some pressure tests on the billet block on both the GPU and the CPU side. Some really interesting maps here. We'll be talking about these for the pressure distribution of the solution. And as for thermals, we wired up a bunch of these calibrated K-type thermocouples to a 4090 FE board. And the purpose for all this testing is because this is a really unique and strange, but in a cool way, product or prototype, whatever it may be classified as right now, where as an engineering exercise, Billet's trying to do some pretty cool stuff, and they're dealing with really high heat applications in a very small, compacted area, which brings with it challenges of dissipating that heat, even though they're using water. So that's what we're going to be exploring. So some basics. We have two variations of the block today. There's the pre-production one and then effectively the production model as stated. And again, this is intended to share some of that design insight between the two as well. The block is made in the UK, and Billet Labs is a small company that's two guys right now. So there's Felix and Dean. Dean's background is in building computers, and Felix's background is in engineering and machining. As we understand it, Dean's probably got some engineering knowledge as well. They work out of a UK-based workshop, and the blocks are being effectively handmade to order, and again, they're made in the UK. The purpose of the block is to do something different. Billet has smashed the CPU and the GPU as close together as possible, creating a sandwich of parts that's bridged by sharing a cooling solution. Sharing a block like this will elevate the overall temperature versus something more spread out, even if it's just tubes separating those blocks normally, and that leads to some unique engineering challenges. The block also must contend with motherboard fitment, which we'll talk about later, although there's some evidence of what we had to do to make it fit that you can see now. But once it's all assembled, it becomes one of the most compact possible assortments of components that can handle this heat capacity. To spoil it a little bit, we were running 1,000 watts through this configuration, and we were well within spec and distant from thermal throttling. So pretty interesting package for the heat it's dealing with. Now, to set expectations, the block isn't engineered to be the literal best block from a purely thermal performance standpoint on the market, but as far as we're aware, it's currently the only monoblock solution that executes things this way. So if you were to throw this onto a small bench platform, like we've done here, we took the other foot off for display, but you can see it's about as small as it can get, or make or get some kind of case for it. For example, one of the frame cases like you see from Montech, then you'd end up with about the smallest possible build with this block. Now this will have stiff competition from Alphacool from a pure cooling standpoint. EK has fallen behind a little bit in recent years where it hasn't updated its microfin design, and that's going to set it back for thermal. So we actually chose Alphacool for the direct comparison to this because it should be about one of the best blocks on the market right now. Here's how the billet block is constructed. The newest rendition of the block fits both a 3090 Ti FE and a 4090 FE, and it's gone through several revisions to tune fitment and clearance. This helps ensure compatibility and also contact with the right board components. Total cost for the block is about $900 US right now, so this is effectively a proof of concept that you'd buy if you had a really specific use case in mind. For the CPU, the kit can be installed for either Intel LGA 1700 or AMD AM5 or AM4. The block uses a kit of 4 washers to isolate the 4 standoffs from the motherboard, some screws to press the CPU block into the IHS, and then a set of washers and screws to flip the GPU and sandwich it against the opposite side of the block. The block is entirely made of pure C101 copper, including the pipes that connect to tubing and fittings. The choice of specific copper supply is expensive, as is the choice to make it in the UK, and the lower volume contributes as well. This is not a factory mass production scale product yet, if it ever will be. Let's go over installation. The installation process is slightly different between our earliest prototype and the more recent model that we have, but overall the steps are pretty similar. First of all, it's more involved than a traditional set of water blocks. Makes sense. It's an unorthodox solution, and they all connect together. So that requires special attention. On top of that, there's some planning that you would need to do if you were going to install something like this, and that's because there are a couple potential pitfalls the user should be aware of. One of them is VRM heatsink clearance on the motherboard. This is something that Billet is forthcoming about, and actually one of their main sort of points that they market on their website is they want to be available to anyone who reaches out to them for custom solutions, and that includes checking the fit for motherboard compatibility. So they're kind of mixing that, call it a white glove service or something, alongside the actual billet block. So it needs some planning, especially for the VRM heatsink. We won't cover the preparation steps in detail, like disassembling the GPU down to the board, but one key note is that any M.2 drives and RAM should be installed to the board first, as adding it after assembly may be difficult or impossible due to restricted access to the motherboard from the block. So the most recent unit we have came in this wooden box, which is part of the retail package, including the burned-in code on the top. The block was pre-assembled for shipping, along with the necessary washers and screws, and there's an extra set of gaskets included, and Billet Labs also has free DXF files available for use for those who have laser cutters. The tools and supplies a user should have on hand for installation include a 2.5mm and 2mm Allen key. Both are in our GN teardown toolkits on the store, thermal paste, a spreader, tweezers, rubber gloves, and included wooden sticks. The gloves are to prevent oils from the user's hands from getting onto the raw copper, which can tarnish the surface. And the monoblock is composed of 3 main elements: the motherboard backplate, the main monoblock assembly, and the GPU backplate. The monoblock's main body is composed of several pre-assembled parts with delicate oil paper gaskets that Billet doesn't intend for the user to need to deal with. Disassembly beyond this point is definitely not recommended, as you could disturb the gaskets and potentially render it more vulnerable to leaks. Installation starts with laying the copper backplate on a table and resting the motherboard on top of it. Next, we place a new set of washers on the board over the backplate screws. The original unit we tested used thin translucent washers here, whereas the newer unit has thicker black washers. The long aluminum standoffs thread onto the backplate screws in a cross pattern. After applying thermal paste to the CPU, the monoblock's main body gets lowered onto the CPU and standoffs. The fit between the standoffs and the monoblock is precise, and care should be taken to ensure that the monoblock is fully seated on all 4 standoffs. Once the monoblock is in place, it gets secured with 4 M4 screws with 2.5mm Allen heads. There are no springs for any of the mounting points, so there's a very abrupt change in resistance once the screws bottom out. Billet told us that it's working on a recommended torque spec for all of its fasteners, but in lieu of those, we attached it like any other hand mount cooler and just stopped when we hit the wall of resistance. Next up, maiming the motherboard, specifically the heatsink. A major point to be aware of is the clearance between the inlet tube and any VRM heatsink on the motherboard below it. Per Billet's manual, our original prototype has only 25.5mm of clearance between the bottom of the inlet tube and the surface of the motherboard. This wasn't enough space for the finned VRM heatsink on our Gigabyte Z790i Aorus Ultra, so we made it fit. The manual states, quote, "You may have to remove or modify your VRM heatsinks for the monoblock to fit some boards. For our situation, we had to remove a small decorative plastic piece and bend the fins out of the way to let the inlet tube clear." This is obviously less than ideal to require a user to do, and it's a big request for most people. If the inlet were just a few millimeters higher, it would have cleared our board, but for now, it's not. We asked Billet about this, and they said that the inlet position is relatively locked in, for now at least. However, they could change the way the copper pipes and the pipework are soldered. So if someone had a specific request to do it a different way, maybe they could do it at an angle instead. Current customers will receive their kit just like we received ours. Future ones may get a revision. Billet, however, noted to us that any customers can reach out and discuss a reconfiguration of the pipework or a fit for a specific motherboard if that's something that you need to accommodate, or if it poses a major problem with your build. Continuing with installation, the prototype we got came with hand-cut and hand-labeled thermal pads for the GPU, all of which are the same 2mm thick material. The pads included with other GPU blocks, like the Alphacool Core that we put up against Billet later, are often thinner. There's a lot that goes into thermal pad selection by a manufacturer, but as a rule of thumb, thinner pads are usually more effective at transferring heat. There's less material in the way, whereas thicker ones give more tolerance. One thing we noticed was that Billet's original instructions didn't have the user place pads on the power stages for the VRAM. But after we asked about this, they immediately made an improvement to include direct contact with the memory VRM. This was done in a matter of days and was a speedy response. The VRM would still have been within spec, but it's ideal to have thermal pad contact, and it does now. After all this, some thick washers are used on the GPU side of the monoblock over the interior vacant holes. From here, Billet advises placing 4 of the wooden sticks or toothpicks down into the holes to assist with keeping all of the components on the GPU side aligned during assembly. It'd be easier if there were adhesive on one side of the washers, or maybe a machined area around the screw hole to help keep them in place, but this works for now. Next, after spreading thermal paste across the entire die, we flipped the GPU PCB over and carefully aligned the 4 mounting holes with the toothpicks sticking up from the monoblock. Finally, a second set of thermal pads gets applied to the backside of the GPU, and the last set of washers marked C gets placed over the 4 mounting holes before carefully lowering the thick copper backplate into position and removing the toothpicks. There are 2 sets of screws to choose to sandwich the GPU side together, either stainless steel with 2mm Allen heads or brass with slot heads. At this point, the assembly for the monoblock is finished and a PCIe riser cable gets put in place. We found installation to be overall easy, but it's definitely fiddly at times, especially with having to use these sticks or toothpicks to kind of hold everything in place vertically down the center like a column. So that was the only part that could be frustrating if you lose track of one of those washers in there. But the packaging was extremely well marked with letters assigned to everything to make it easy to find. Okay, let's get into testing. So this requires some explanation of our new setup, which is over there. We'll have some footage of it. This is really exciting actually, because we introduced a new custom loop test platform for this process, which means now we can review custom water blocks, whether that's CPU or GPU, provided it fits on the components we've chosen. We built this brand new test bench for this piece, including this massive 9x1 20mm radiator with integrated reservoir and pump unit. We're using quick disconnects for ease of operation, so we went with a dual DDC pump to make sure that the flow restriction isn't going to hold us back in any scenario. The overall goal with this is to remove the cooling capacity of the radiator, the performance of the fans, and the pump from the equation as much as possible. We're trying to isolate variables here. Flow order has the coolant start in the reservoir, go to the pumps, into the radiator, out to the system, and then back to the res. The PC itself for this test platform uses this Z790i motherboard from Gigabyte, and for the CPU we're using a 13900K, for the GPU we're using a 4090FE. For the configuration, we fixed the voltages, the load line calibration, and the frequency of the CPU, so it's completely controlled. There are no automatic changes that are relevant under control of the motherboard at this point, or the CPU, and that produces about a 300 watt load or so. For the GPU, we've fixed all of the clocks for that. We've done some tuning custom for it, and that's running at about 600 watts, completely fixed and controlled, so it won't be changing. So combined, we're looking at about a 900 watt load if running a full system torture. We also have isolated loads, so we have an isolated 300 watt CPU load, isolated 600 watt GPU load without the other component doing much of anything. Testing's automated, as most of our thermal testing is. I wrote a custom script that executes a mix of basically Blender and a GPU load program, and then those together are what produce the combined load. Methodologically, we're doing multiple mounts and test passes. We do this for all coolers review, so this comes from our CPU cooler testing methods, where we do a minimum of 3 separate mounts, so that allows us to account for human error or differences in the mounting process. And then for each of those mounts, we do at least 1 pass, but I think our total passes on this is 10. As for the thermocouples that are sticking out of this, so these are needed in order to monitor temperature of board level components. This is important because for something like especially the Alphacool Core block, which has full channels all over the memory and the VRM area, we need to be able to measure those parts of the board to make sure they're actually being cooled well. That's part of the marketing of one of those blocks. And since those temperatures aren't surfaced, what we end up doing is wiring these K-types to MOSFETs. So we have one on a MOSFET near the I/O side, one on a MOSFET on the other side of the VRM. We've got, I think it's 1 or 2 on memory modules, plus the internal sensors from the video card itself. And finally, the whole thing is completely self-contained, which is the awesome part, because now we can get into reviewing custom blocks if we want, outside of this benchmark feature where we could look at things like EK solutions next. They'd be directly comparable to the Alphacool ones we ran for the comparison here. So let's talk about the head-to-head. We picked up the Alphacool Core 1 CPU block and the Core 4090 FE block. These are both high-end blocks that should represent somewhat normal custom loop parts well. As we understand it, these should both outperform EK's primary choices at the moment, but we haven't looked at those yet. We also ran some tests on a Deepcool LS720 360mm CLC for comparison to an off-the-shelf cooler, and we'll start the thermal testing with a few different load conditions. Let's start our thermal charts with a GPU-only workload. This will feature a Founders Edition 4090 with its air cooler for comparison, a pairing of Alphacool Core CPU and GPU blocks, and 2 variants of the Billet Monoblock. The CPU is not doing any work in this test, only the GPU. That means our total power load is about 600 watts, plus maybe 100 watts of background load from the CPU tasking the GPU. As for the changes between the prototype and the production model, the prototype used 0.3mm fins with 0.3mm gaps, whereas the new block uses 0.3mm fins with 0.5mm gaps. This change makes this block manufacturable with Billet's current tools and suppliers, and as the prior configuration had under 50% yields, it was a necessary change for production viability. So our testing will look at whether it impacted the thermals. They also made changes to the gaskets and the water tightness, which are good changes. They said, quote, they increased the gaskets from 0.15mm to, in order from CPU to GPU, 0.4, 0.8, and 0.4mm. They also said they test each block with air to 12 psi for 5 minutes before dispatch, which was in response to some testing we did on pressure. Here's the chart. The Billet pre-production block is represented in blue. Red represents the most recent revision, orange is for Alphacool, and green is for the Founders Edition air cooler. GPU idle was about the same on all the liquid coolers, at 2 degrees and under for delta T over ambient. The GPU load temperature is put into perspective by the FE air cooler, which itself does well, but is obviously nowhere near liquid performance. We measured 50 degrees delta T over ambient. The Billet block was 29.5 degrees DT over A on the pre-production unit, with the denser but largely unmanufacturable microfins, and with the newer, more spaced out fin design, it was at about 31.3 degrees. It's not a bad loss considering the significant change in fin density and the 600 watt load. Alphacool's Core block ran in between the two at about 30 degrees, so Billet's in good company here, especially for a 2-man team with the first product. GPU Hotspot posted similar performance with the ceiling set by the FE card at 60 degrees over ambient, or a delta of 10 degrees core to hotspot. For water, the original block did best, but that's irrelevant if it can't realistically be made at scale. The new block only sacrificed about 1 degree of performance. Alphacool and the retail Billet block are about the same, which again is good news for a company making its first product and being still sort of in a prototyping phase. The delta matches what we saw in the air cooler delta. Now for the same GPU-only load in the loop, but looking at the memory and the VRM sensors that we installed. This is where Alphacool's experience shines through. It leads the Billet block significantly in these categories. However, all components are well within spec and nowhere close to a level of concern. The FE card sets our reference point to that. It is also well within spec. When air-cooled, it was already under control and in the 40s for delta T over ambient, meaning in some of these cases we have 60 degrees of thermal headroom to run even hotter if it needed to. The Alphacool block sits comparatively impressively in the 14 to 22 degree over ambient range. As for Billet, the original block did better for VRM hotspot near the I/O, but the new block did better for some of the memory modules. You can see this in the 22 degree versus 27 degree mem write entry, where better contact force and squish on the thermal pad of the retail unit improves performance. These results are acceptable, but also indicate Billet's primary place for improvement for future revisions. And speaking with the team, they've been hard at work to further bolster VRM and memory thermals. Let's switch to a CPU-only load. With the GPU idle, we fed about 300 watts of CPU load into the loop and blasted power on the 13900K. This is tested using a Deepcool LS720 closed-loop liquid cooler as a baseline reference point, but for that one, we kept the Alphacool block on the GPU. Just obviously wasn't the same loop. Here's the chart. The LS720 set our expectations by establishing a 65 degree average P-core temperature over ambient, or 57 degrees for all cores averaged at steady state. All the custom water blocks outperformed this, which is good news for custom loop components. Alphacool had the best performance here at 51 degrees P-core and 42 average all core, although this is a relatively wide delta. Billet's pre-production block with the denser fins ran at 57 degrees over ambient, with the production change that benefited GPU memory temperatures increasing the CPU temperatures in this particular load, moving it up 3 degrees. That's still cooler than the CLC, but the manufacturing trade-off had thermal considerations closest to the cores, which makes sense. That's where they changed the microfins. Now we're moving to a full system torture workload. This will be difficult for it to maintain. We're running over 900 watts for this. We have an overclocked GPU at 600 watts, overclocked CPU at over 300 watts. The large radiator and the liquid capacity help to ensure that we are more limited by the blocks and their ability to deal with and spread the heat and dissipate it than we are limited by things like the radiator. And remember as well that the increased overall sort of residency of the heat as would result from less dissipation and removal of heat from the system means that all components that are being tested here will report higher temperatures. So for example, a higher GPU core temperature means as well that we'll be contributing to a higher GPU memory temperature, especially because both of the components are sharing a cold plate, whether that's Alphacool or Billet. Here's the GPU thermals during that load. GPU load was about the same on all tested devices. The original Billet block outperformed the Alphacool solution when under this combined load, whereas the new one was about 1 degree warmer, roughly margin of error. GPU hotspot was within error as well, more or less, and water temperature was about the same in all tests. Once again, considering the team's greenness and considerable concentration of heat in a small, fully bridged area, this is a good result. Now for the component temperatures. Once again, Alphacool proves itself competent in this regard. It runs the coolest individual GPU component temperatures, definitely in part thanks to slimmer thermal pads in combination with water flowing through channels that are over these components. Alphacool's GPU memory is significantly cooler at 24 degrees and 19 degrees over ambient, and this is a company that has a lot of experience making GPU blocks, and it does have that extra channeling, so this makes sense. Billet is well within spec and significantly cooler than the air cooler, but clearly has the most room for improvement here if it wants to compare against standalone blocks. The new Billet block was cooler for the right memory module once again, although not by as much as when the total power was lower. The VRM hotspots run warmer than the original block, which is partly due to the reduction in performance in the microfins, causing more heat to accumulate in the area. And the CPU result from the full torture test shows us where that heat gain came from. Here, the deviation between the CPU and GPU widens from what we saw in a single component load. The Billet block increased by about 6 degrees for all core temperatures averaged at 59 to 53 previously, with Alphacool holding a significant lead at 48.8 degrees over ambient. Performance is still acceptable considering the massive amount of heat and considering the density with these two parts sandwiched together. Time to look at pressure distribution. This is tested using a special contact paper and NIST traceable scanner that our community helped us purchase with support on patreon.com/gamersnexus and on store.gamersnexus.net. Your direct support on Patreon is what helps us fund these advanced testing efforts and equipment purchases and annual calibrations. Purchases of our mod mats, our soldering and project mats, which are extremely heat resistant, and shirts on the GN store also directly fund this work. Here's the map of the GPU pressure distribution. Pressure scans look at the quality and placement of mounting hardware. Alphacool's core GPU block is at the top and Billet's block is at the bottom. Alphacool's block has the most contact at the top and bottom edges of the GPU, with weak contact centrally. This is an okay overall map for Alphacool, but the mounting hardware doesn't provide the most even distribution across the GPU silicon, and it's especially lacking centrally where it matters the most. Billet's prototype, shown in the first two scans, had heavy contact at the left edge and overall more contact than Alphacool, but it had weak contact in the top right. The most recent scan that we performed on their most recent retail block, which had some mounting hardware changes to the washers and some screw length changes, provides the best pressure distribution we've ever seen on a GPU. The mounting pressure is phenomenal here, and they've really done an impressive job tuning the pressure distribution. This will help make up for the wider spacing of microfins and the shared solution between the CPU and GPU. Now for the tricky one. We'll start with the prototype comparisons to Alphacool's Core for CPUs. First, our initial scans. Alphacool's CPU contact is heavy centrally and along the top and bottom edges. You can tell this is an Intel CPU just by looking at this map. This is exactly where a contact plate would help with pressure distribution. We've shown that in past videos. Overall, though, Alphacool's contact is good, and it's limited only by Intel's independent loading mechanism and integrated heat spreader designs. Billet's prototype is shown in the first two columns at the bottom. Billet is overall about the same for these initial installations. It's pretty close to what we're seeing with Alphacool. It's a little bit weaker in the center and higher at the top and bottom edges, but overall they're comparable. But there's one scan that we spent 8 hours validating, and it's this one. We actually did this multiple times and we got the same results. This scan is of the production unit from Billet after it had been mounted and dismounted a few times for our test passes. Pressure is low enough at the center that we'd be relying really heavily on pace to bridge that gap. There's high pressure at the top and bottom of the CPU. Remember that white doesn't mean zero contact, but definitely the pressure is way below what's desirable here, and this is poor contact. It's actually some of the worst we've seen for a CPU contact patch. As for what happened, we had to use our laser scanner to figure that out. In this testing, we used our new 3D scanning analysis machine to scan in the cold plate of the CPU and the GPU sides of the block. This is about a $60,000 machine that uses a laser with repeatability down to 0.05 microns on the z-axis, and will soon replace our needle tester for CPU cooler flatness testing, so you're going to see it a lot more. And again, it's your support on Patreon and the store that makes these things possible. For this testing, we have to spray the cold plate with a special anti-reflective chemical to allow a clean laser scan. The impact results is around 1 micron and is irrelevant. We performed this testing after multiple mounts and benchmarks, so we're seeing it after any natural deformation that occurs as a result of using the mounting hardware. For this testing, we deployed 400 test sample points across the surface of the contact patch for the cold plate. You can see those represented as red averaging sample dots in this clip, although more samples in total were collected than just here alone. The highest to lowest range of results on the GPU cold plate, which is the one you're looking at, is about 33 microns. Overall, consistency point to point is good. This makes sense considering the impressive GPU pressure we saw. In this clip of the CPU block, you can see our sampling area is approximately where an LGA 1700 CPU would be. The result is 25 microns max to min flatness. This is overall also flat, so the CPU pressure problem isn't from the contact patch flatness itself, nor is it deformation of the contact patch itself. This did point us toward the issue though. The CPU cold plate is so rigid and flat that the rest of the block deformed very slightly at the 4 mounting points, which reduces the pressure centrally on the CPU. In fact, we had to magnify our scan 100 times to be able to even see the impact because it's so minor and spread out. This is a massive magnification of the scan to help human legibility, and here you can see the block is very slightly rounded inward. We can also see in the magnified CPU scan where it's slightly bowed. Again, for the CPU contact patch, about 25 micron range. It's not much, but the point is that you can see it deflected across the block. Overall, the flatness of the contact patches for the CPU and the GPU both are impressive. It just means that because those contact patches are so rigid, something has to deform a little bit, and it ends up being the points of contact for the mounting kit. Performance was good. We saw the numbers already, and they're doing fine. It's just that this is an area that Billet can improve. If they can increase the mounting pressure to the CPU, it might increase the performance a little bit, getting the heat away from the CPU that much faster. But it's not the flatness that's the problem, it's the weakening of the pressure that becomes the potential impact to performance for Billet. Wrapping this up, Billet has some key areas of strength and key areas of weakness, and we'll kind of recap this the same way we did for the recent Starforge pre-built that we reviewed. So the strengths first, these include the compactness of the overall package. Obviously, this is exceptionally small, and that's pretty cool. You could do a lot with this. If you're a creative builder, you may have avenues to really do something unique. Especially if you're into maybe modding or fabbing anything custom for it. So there's a lot of positives for the form factor. Now, GPU pressure on the technical side is the most impressive thing that they're doing here, where we have genuinely never seen a pressure patch that good and that consistent on any of the GPUs. And back in the 30 series, we did pressure maps on almost every partner model card that we looked at. And this still is the best one we've seen. So that was really good. The surface flatness is also remarkable. Thermal performance was classifiable as good for the GPU and the CPU core components. Very competitive there. It's directly competitive with basically the best 2 water blocks. that we're currently aware of in sort of the retail-ready market, the mass production market, being Alphacool for those. We also think that the two guys running the company have a good attitude towards refinement and improvement, and that is important for a company that's small and kind of getting started because the attitude's going to matter. In terms of areas that need the most improvement, so we have a couple of those. The first is the non-core temperatures. So looking at those thermal charts, clearly the biggest place that Billet can improve is going to be in the VRM, the power stage temperatures, a little bit in the memory temperatures, but it's really the VRM where there's a big gap between them and between Alphacool's core solution. So Billet, overall, they're doing fine here in that they're still better than an air cooler. It's just that if they want to directly compete with big liquid cooler brands on the market, that's going to be probably their first area to really refine. And they have the most room for improvement there. We think a lot of the advantage that Alphacool holds in its testing was that it's got the water channeled over the memory, over the VRM directly. It's probably benefiting Alphacool a lot here, and that's something that maybe Billet could look into, but it complicates the block a lot, and we're not sure how it affects the compactness of the form factor. Additionally, next area for improvement would be the deflection of the block after repeat installations. This indicates to us that maybe some strain relief could be designed into the block or the hardware somewhere, or just an area where it's weaker intentionally. It's not crucial. The thermal performance was still overall good, and it seems unlikely most users would put these through the amount of mounts that we did, but we think there's some room to improve CPU thermals if they can minimize the impact of deflection to CPU mounting pressure. It's also clear that Billet is still learning. It's a small and new company, and that really shows through in some areas of design more than others. One of them was the running change where they added thermal pads to the memory power stages during the course of our testing when we found and asked questions about it that they were lacking. So it's good that they're making those changes. They're quick, they're responsive to them, that's awesome, but it's also a good reminder that, hey, this is a new company, they're still figuring things out. That said, we've seen EK do the exact same thing, so there's always room. There's always room for every company to improve. But Billet has also made a running change after our work on the prototype, where the retail model is now improved in a couple key ways. So we were running 2 pumps at extremely high speeds, creates a lot of pressure. The original prototype developed a slow leak where a couple droplets of water exited. This was after we were running it for a few weeks, I think it was, during testing. So it was under a lot of load, a lot of continuous pressure. Within a day, Billet responded to this research, and they immediately made revisions for the retail unit, which is what we have here, and those changes were sent to us. The changes to the gasket and the mounting pressure have, at this point, all survived our very high pressure testing scenario for something like a month now of on and off work testing, so it's resolved. So that's good too. They do react very quickly. Price is the biggest challenge for this, so we think the most suitable user would basically be an ultra enthusiast who really wants this super compact form factor and maybe has an idea for a mod or a custom build of some kind. And the performance, again, for the core components was really impressive to us considering what they're doing with the block and the experience level of the company. So they've started in a great spot for core thermals. And for value, it's clearly not marketed on value. It's marketed on being something cool, but it clears the bar for performance. So one of the other things, too, is they have an 8-minute video on their YouTube channel about how they hand polish and hand deburr all of the units that go out, including the retail units that are purchased. So there's a lot of manual labor that goes into this block at this stage. You'd be buying this because you want something cool and unique and you have an idea for it, not for just pure sort of cost to thermal benefit. The most important piece is that they've cleared the performance bar in most areas for what started life as a concept. And this seems like the kind of product you could really easily screw up in big ways thermally and get terrible numbers out of it, but they didn't make those mistakes. So with the VRM improvements maybe locked in the future as well, they'd be in a pretty good spot. So that's it for the engineering dissection of the Billet Labs Monoblock. It was fun to see the R&D process. The pressure map for the GPU is now going to be our reference point for what is the best possible pressure map we've ever seen. So that was cool to get out of this as well. And we're not sure where Billet will go from here, but the attitude is right, and we're looking forward to revisiting their potential future offerings because they have a chance to really do something in water cooling potentially. So we're looking forward to covering more of it. And that's it for now. Thanks for watching as always. Our understanding, by the way, is that Jay's2cents is working on a build for this. He posted a video just kind of showing the block, and you all know that he does crazy custom builds. So we're looking forward to seeing what he does in that department with it. You should check it out. Thanks for watching. Subscribe for more. Go to store.gamersaccess.net to support us directly, and we'll see you all next time.